Well, thank you all for joining me here today. It looks like we've got a pretty good showing in the room, and I can't see the chat window, so I'm not sure how many people we have online, but it's a good showing there as well. Thank you. Yes, I'm Rafael Lugo. We'll go ahead and jump to my next slide. I'm from North Carolina. I've been at Langley since about 2007. I went to NC State. I see a couple, actually before I started, I saw a couple of my friends from NC State online, so it's good to see them. Go Pack. But the reason I bring that up is that when I was doing my graduate work at NC State, I was actually here at the National Institute of Aerospace at the street. And while I was there, I had my office in 1209, so I've actually been on site here at Langley since 2007. And since 2008, I've been part of the Atmospheric Flight Entry Systems branch, so they haven't gotten very good of me yet. Since then, since I graduated, I joined Analytical Mechanics Associates. While I was there, I worked, I did some work for NESC, doing SLS launch and ascent IVB. I also did a lot of work doing flight mechanics and GNC analysis for human scale Mars lander systems. And I'll talk a little bit about some of this stuff later on in this talk. Since 2019, I've been a civil servant here at Langley, same branch, D205. I've been for, gosh, I don't know how many years now, a couple of years now, 3, 4, it kind of blurs together. I've been the flight mechanics integrated performance simulation lead for HLS, HLS Artemis. I've been working with NASA and with SpaceX for their initial lander for the moon. I've also been the Post 2 development lead. I'll be talking about that in a little bit too. It's one of our simulation tools here at Langley that we use extensively on D205, and I've been the dev lead for about 1.5 years, I think now, but blurs together too. So I wanted to kind of give a little bit of context of what I'm talking about. So if you saw the lecture title, it's Advances in Flight Mechanics, Modeling and Simulation, which is very vague. And obviously, I'm not reporting that I am the final say in that sort of thing. I'm just trying to give you my view on this topic. And so to give you a little bit of background first, back in around 1995, 97, during Mars Pathfinder development, there was a team at Langley that was assembled to put together and assess EDL performance along with JPL. To give you a little bit of context, I was in 5th grade in 1995, so I was not part of that team. Very much precedes me. But at the time, it was understood that you've got your vehicle, you've got your trajectory, your GNC, your aerodynamics, your aero heating, all these different things, all these different disciplines and effects were really closely coupled. And the previous Mars mission at the time, Viking, which was back in '76, was an entry from orbit system. And Pathfinder was designed to be a direct entry, so the heating environment, the aero heating environment, was much more aggressive. And so those kinds of differences and the resulting concerns really led to the idea that why don't we put a lot of these multidisciplinary models into a single simulation framework? So at the time, that was a program called POST, which I'll be talking about again. And all of this is documented in a JSR paper that I've linked here. So the approach that was chosen by this team was really to blend all these different disciplines, all these different engineers, flight mechanics engineers, GNC engineers, system engineers, as a cohesive multidisciplinary unit. And that kind of approach, this kind of end-to-end integrated performance analysis, I'll talk a little bit about what that means, has shown over and over that it can provide really good, enhanced, improved insight and understanding of flight systems that are really becoming increasingly complicated as time goes on. Mars Pathfinder, that was '97. Mars 2020 landed 1 or 2 years ago, and things are just getting more complicated. And when I talk about more complicated, not just the flight system, we're doing Monte Carlo statistical analysis, we're looking at system faults, trying to answer what-if questions. And what that means is that we don't just look at a single flight phase. We don't look at just power descent. We don't just look at entry. We don't just look at ascent. We don't just look at the nominal. We look at it as a kind of combined, that's that end-to-end part, integrated performance analysis. So in the past, historically, this has been pretty computationally expensive. I was actually just looking at a shuttle guidance report from '83. And they were talking about doing Monte Carlo runs with 50 samples. I don't know if that was I presume that's a hardware technology limitation. Now these days, the group that I work with, we typically run 8,000, 10,000 case Monte Carlos, if not more, just to give you an idea of kind of from that aspect, what has changed. But obviously there have been changes in the past 10, 20, 30, well, since computers have been computers, there have been changes in hardware, software, and these changes and improvements can lead to obviously improved runtime, but also possibly improving our levels of fidelity in our modeling and simulation. So how do we take advantage of that? How do we apply these advances to the kind of framework that we've built up over the years and keep our flight validated heritage? But before I get into that, flight mechanics, modeling, and simulation. So again, as I said at the very beginning, that's a very broad statement. If you were to ask 10 different people what that was, you would probably get 10 different answers, and none of them would probably match what I'm about to tell you. So, some people will say flight mechanics is 3-DOF trajectory optimization. Some people will say that flight mechanics includes 6-DOF dynamics. Other people will say it includes GNC. I've heard the whole range of descriptions. So to me, and I want to emphasize this is kind of my viewpoint that's been shaped over the years working with this group. I think we're saving questions.
I just need to know, what is GNC?
Oh, guidance, navigation, and control.
Okay.
Yes.
Thank you.
Thank you for pointing that out. Yeah, so all these different pieces, to me, flight mechanics is really, in the end, a very broad field and can include bits and pieces, elements of all these different disciplines. And so for the purposes of this talk, you're free to dispute this, I encourage you to, but for the purposes of this particular talk, I'm going to say that flight mechanics is a study of the performance of the integrated system of systems that make up a flight vehicle and its environment. So that's coming from the idea that you really want to look at for these complex flight systems, you got to look at it as a whole, the system of systems, integrated performance. So to me, that means basically everything. 3-DOF, 6-DOF, trajectory optimization, aerodynamics, air heating, propulsion, manual control, off nominal, forward snares, everything. So if you bear with me with that for a little bit, then yes, there are many, many, many tools out there that exist that can look at different parts of flight mechanics. We've got things like Copernicus, QuickShot, Lazarus++. We've got folks from the team at one of my sister branches that look at this kind of stuff as well. Many, many different tools out there. And I'm going to give you an example based on my experience on HLS. So I work, as I said, I'm the flight mechanics integrated performance simulation lead for DDL. I don't know if I mentioned that. That's G-orbit descent and landing. So we look at the kind of very last bit of the trajectory. But for HLS, we've got multiple simulations looking at DDL. We've got Post2, GLASS, Lazarus++, Copernicus, Linko, all these different tools. This is not a comprehensive list. There are many, many other simulation tools on HLS that are being used. This is just kind of a snapshot. And they are from different disciplines. They do different things. They have different focuses. Some tools focus on different phases. Other tools are very much focused on, let's say, frequency history or frequency domain analysis for controllers. But for this talk, I'm going to focus on one, the one I'm most familiar with, because I happen to be the current dev lead, which is Post2. That's the program to optimize simulated trajectory routine. What is Post2? Well, this is an eye chart, but I try to put a cool animation in there to distract it from that. The boilerplate statement we've got is that it's flight validated, a generalized, event-based, point mass, vehicle and trajectory simulation code base, which is kind of a mouthful. But what that means is that it's a 3-6 multi-DOF simulation tool that we use for analyzing and assessing flight mechanics problems. We develop it here at NASA Langley Research Center, right out of my branch, D205. We follow a developers as users approach to development, and I'll talk about that in a little bit more detail in a moment. Some of the key features of Post2, it's input deck based. I think input deck goes way back to when it started, when they actually had decks for inputs, punch cards, which very much predates me, but I've seen them. Well, of course, they're now, the input decks are all now ASCII digital files. It's got its own robust custom input language for those input decks. It interfaces with multidisciplinary models provided by the user, such as flight software. This kind of graphic here shows you the kind of models that we interface with generally on a regular basis for different projects. Built-in trajectory optimization, that's the O in Post. We wouldn't call Post without it. It'd be called something else that I don't know if it's right for me to say. And very recently, in the past, really in the past year, we've been working on an API that lets external tools, such as Copernicus, call post and optimize on it directly. So you're treating post as the dynamics driver in other tools. We'll talk about that more as well here in a minute. Some key applications, I've talked about integrated performance, statistical analysis, Monte Carlos, orbital atmospheric trajectory optimization, GNC algorithm development. We look at fault supports, margin analysis, so all kinds of fun things that we look at. Sample products. I wanted to give you an idea, having said, those key applications, what is an example of what we do on a project? Well, again, I'm going to go back to my example of HLS, which I'm most familiar with. The simulation products are cross-disciplinary. We talked about the models being multidisciplinary. The products are also cross-disciplinary. So here you can see for HLS, we've got flight mechanics, GNC, guidance, navigation, control, structures, communications, crew co, which is what HLS calls the crew compartment, or kind of the crewed part of the system. Induced environments, that would be, plume surface interaction effects. So the products that we can deliver to these different teams and these different multidisciplinary teams are useful to them, but to be able, in my view, to be useful, the sim developers and analysts, which in our case, I'll talk about are kind of the same folks, have to have some level of knowledge in those disciplines. And so to me, ownership of inputs and outputs is key to this approach, this multidisciplinary, cohesive unit approach. So, there's no finger pointing, there are no black boxes. Nobody says because the algorithm said so. We have ownership of the work that we're doing. And so to me, I call that, this is a very marketing buzzword, which I've heard nobody else use in my group, but I'm starting to use it now, vertical integration of the software development and flight mechanics analysis. So what does that mean? Well, very often, if you use an engineering tool, or really a lot of other software, you probably look at it as a black box, whether you realize it or not. You don't really see code, you don't compile Microsoft Word, you don't debug Excel. If something goes wrong, you probably open a ticket with the developer. You send them an email or you go online and say, hey, something's going wrong, help. That model is not followed by the Post2 developers, by us. We write the code, our team compiles it, we use it. That's one of the key points that I'm going to be talking about. We try to limit the use of external libraries when possible, but that's not always, can't always do that. But in general, if something goes wrong, we're the developers. We go to ourselves to fix a problem. And so if you look at this, what I'm trying to say is the vertical integration. We own every step of this development process. We design the system, we design the software. New features are talked about in our development team meetings that we have every other week. Implementation. So we often, if there's a new feature, it's going to be prototyped both by one of the aerospace engineers. Production versions of those features are probably going to be implemented by software engineers. Testing, we do continuous unit and regression testing. We have project level testing where we regress against flight projects. Distribution, we develop internal versions that have kind of in development engineering models, and there are external versions that we release that you can get online on our website. And then the last step here is the analysis. The same team that does this work for development also does the analysis. Flight projects, ground tests, proposals, research, it's all that's that vertical integration that I talked about. We own every step of this process. Now, there are exceptions. I'm kind of being loosey-goosey with my phrasing here. A lot of times we will receive delivered code, we'll receive flight software. And for those kinds of situations, obviously we don't write flight software, but we work closely with model authors to make sure that we have to verify the implementation, to make sure that it's implemented correctly. So, state of the Post2 codebase. I've talked about how, I don't know if I've talked about how old Post is. It's very old. It goes way back to the 70s. It's been used, it was originally developed to support shuttle. It's been used to support all NASA Mars EEL systems, except Viking, so everything Pathfinder and onward. We use it to support SLS, commercial crew, CCP's commercial crew project, HLS and Artemis, numerous ground and flight tests that I can't rattle off here, but here's a sample, which I don't expect you to read, but these are all papers, conference papers, journal articles that have been published since 1998, I think. 1988, good Lord. 1988, 1985. that in some way use post as doing something for some analysis. So that gives you an idea of kind of the scope or scale of the different kind of projects we've worked on. The newest version, which I think is 4.4, is really cleaner, it's more robust, and more flexible than really any previous version. That's by design. We're trying to clean it up. We're trying to make it cleaner. We talked about versions that we distribute. Those go to other NASA centers. Those go to DoD, industry, academia, really all over the place. But like I said, it goes back to the 1970s. It's based on shuttle heritage Fortran code from the 1970s. Obviously, we talked about programming standards, compute hardware, paradigms have changed drastically, immensely since then. I think in the maybe early to mid 2000s, the whole code was overhauled to be completely C and C++ based from its original Fortran. And what I'm going to talk about here in more detail are more recent efforts to modernize the code to take advantage of more modern compute systems like HPC, which I'll talk about, APIs, multi-threaded systems. So, thread safety updates. I'm going to talk about a couple of different updates to the code, and then I'm going to talk about an actual application that we've applied this to, and then we'll wrap it up. So these slides are adapted from a presentation that my colleague Anthony Williams, I see him out here in the audience, is presenting at SciTech. I'm one of the co-authors, so I didn't feel too bad stealing these slides. So I'm going to throw some buzzwords out here. High performance computing, HPC. It's all all over. You hear it. I consider it a buzzword, but it's a rapidly developing field. For the purposes, or in the context of flight mechanics, it can accelerate development and implementation of GNC algorithms. It can accelerate implementation of optimization algorithms. And as I'll show you in a minute, it can really enable interoperability with other applications that utilize HPC. So if you have an HPC piece of software, perhaps it's not as useful to you if it's interfacing with other pieces of software that are not HPC enabled. So previously, up till now really, Post as a program couldn't really take advantage of these types of systems because it wasn't thread safe. Well, what is thread safe? That means you can have multiple threads performing calculations concurrently, and you get the output that you expect. That's kind of the really simple version of what thread safety is. Post was structured so that you really had global memory addresses for the program, for the vehicles, for the trajectories. That was very not good for thread safety. So we fixed it. We re-architected the program. We encapsulated these memory structures so that they don't share memory addresses. I do have slides in backup that go into a little bit more detail, but I'm going to show you what happens when we actually did this, what we get out of it. It doesn't really sound very exciting until maybe you see what we can actually do with it. So now that Post is thread safe, we can now perform optimization problems in parallel. Well, what does that mean? So the default optimization scheme in Post is a projected gradient method. Those of you that are familiar with optimization know that very often in some of these cases you have a Jacobian sensitivity matrix. You have to build up your derivatives to understand the sensitivities. So to do that in Post, it runs trajectories. The number of trajectories it runs depends on the number of controls. In Post, it's done numerically with finite differencing. So you can do forward differencing, central finite differencing, etc. So previously, before these updates, you had your nominal run. If you consider kind of this line here, this vertical line as time marching forward, you have your nominal run that takes some amount of time. You then perturb your first control to start building your Jacobian, and then you run your second trajectory, so on and so forth. And so all of this has been done in sequence. It's a sequential problem. That's how it's always been done in Post since it had an O in Post, I guess. Now with these changes, we have our nominal run. We still need the nominal trajectory. There's a little bit of overhead needed to kind of set up the problem. And then once you do that, you can run all of your problems, all of your trajectories to build your sensitivity matrix in parallel, limited really only by the number of threads, logical threads you have available on your machine. And so when you do that, it's possible and theoretically to achieve up to a 2x speed in your gradient calculations, depending on the number of controls we have. Of course, that doesn't really happen in practice. There are other bottlenecks and overhead, security overhead that need to deal with. But as an example, this is taken from Anthony's paper, which will be available, I guess, after the conference in a couple of weeks. But to give you an example, I don't really have time to explain all the different details of this particular lunar lander trajectory, But the short story is we have a flight mechanics problem that we looked at where we had a human scale lunar lander, and we're looking at DDL. So we're looking at the deorbit burn, coast to power descent. We have power descent, multiple phases within power descent. We have braking phase and approach phase and pinpoint landing at the very end terminal descent. We broke up that problem, that trajectory, into multiple problems in post, and we can, because of the nature of this particular problem, we can actually optimize different segments of it separately. And so what you see here, problems 2, 3, 4, 5, and 6, we've broken down. Each one of those is some optimization problem with a certain set of controls and constraints, different numbers of controls and constraints. And you can see that in terms of the overall time needed to perform those different problems, we've seen about a 2 to 3 times speed up. In general, it varies depending on the controls you have, over doing it sequentially. So that's pretty, for us, that is a lot. That can mean a lot depending on the number of problems. If you consider trying to do this thousands of times, that kind of savings does build up. There's also we won't get into the weeds here, but there are also differences between the time saved just performing the gradient calculations for those Jacobians versus the overall time. It looks a little better if you look at the gradient calculations here. I'm trying to show you kind of the end results. This is how it takes to do everything, including the overhead. Okay, now I'm going to switch gears. I'm going to switch gears one more time after this, but I'm going to talk about API updates. So this is not part of our talk at SciTech coming up. This is kind of very new. So you guys are seeing this for the first time from anywhere, I think. What is an API? Well, first, before I talk about that, we talked about POST being a pretty powerful all-in-one flight mechanics, trajectory design, trajectory optimization, GNC design tool. There are other, like I talked about, there are other tools. POST is not the only one out there. Other tools are better suited to other parts of flight mechanics. There are tools out there that are better suited to modeling and simulating, say, long period phases of flight, such as interplanetary transfers. If you wanted to model the trajectory of a satellite going from Earth to Pluto, POST is probably not the right tool for that. Well, what if we could use POST as the dynamics driver for some of these other tools for more complex phases? So for example, that orbiter, that satellite I was just talking about, what if that was a satellite that went from Earth to Saturn and then did a Saturn atmospheric entry? Well, a tool that is really well suited to doing interplanetary transfer may not be as well suited for modeling atmospheric flight, which is something that POST is really good at. So what if we could use POST as a driver for those different segments and seamlessly link with these other tools? Well, now you can, or at least we're trying to get there as fast as we can. And the solution to that for us is developing an API, an application programming interface. So that recent development that I was talking about from the past year, we've been focusing on building an API that lets POST be called by other programs. And the key here is that there are no write to disk penalties. So you could do this before. This has been done before. There are papers that we publish on doing exactly this. But every time there's a write to disk penalty, because the only way to communicate with POST is to read from an input deck, to print an out file and read from that out file. And those are all saved to disk. And so you have to have a tool that parses those inputs or populates those inputs, runs the program, and then parses the outputs. And that write to disk is the killer. That just destroys runtime. So we've been testing this in various ways. We've tested this API with MATLAB, with Python wrappers, with Copernicus. And I want to emphasize that it may not be obvious, but really this could not have been accomplished without making POST thread safe first. That really enabled streamlining the development of this API and making sure that it works properly. So I'm going to show you an example of this that I actually really like, because this is, I think, really cool. So we took a test, one of our regression tests that we run all the time with our POST2 test suite. We wrote a MATLAB script that performs the same optimization problem as that regression test. So there's a regression test with an input deck that describes the vehicle, the dynamic, what you want it to do, different events. And instead of using POST's built-in projected gradient method, we said, well, let's use MATLAB and let's use FMACon. If you use MATLAB a lot and you deal with optimization problems, you probably have used FMACon. And so what we did is we had MATLAB call the POST2 API and basically do the optimization process in MATLAB using FMACon. So here's basically the script that we use I don't know if you guys can read that, but there are a couple of different steps here. This is the script that we use to call post from MATLAB and perform this optimization problem. So I don't know if you can see my mouse. Nope, that's not going to come across, I don't think. Well, I'll use my mouse anyway. So you can see that we're setting up variables for independent variables, banks. So here we have 3 bank angles, and one, this value here is actually a timer, I believe. We have the events we want to optimize or have these controls optimize at events 60, 70, and 75 for these 3 bank angles. We set these values using the API from MATLAB. We set up the post to run, again, using the API, calling it as a library. And then if we skip down here, you can see that we've got a constraint. We want to hit a cross range plus 1200, I think it's kilometers. And we set the objective function, which is a reference time out of event 60. And when you do that, this is the part that I think is really cool. You actually get very close to the same answer as post. It's not exact, but if you look at this opt_val variable here, post reports it got an optimized value of time of 127.899 seconds. If you look at MATLAB, it came back using fn_con. It came back with a value of 127.899 seconds, which is pretty darn close. Again, not exact, but I think that shows us that we're on the right track. And there's other things that we can look at, like, it arrived at not quite exactly the same, but very close to the same control values for those bank angles. And again, this is not using post internal optimization at all. It's using post as a dynamics driver. So that's a pretty major step for us. Okay, bring my mouse back. I wanted to touch very briefly on a much more recent thing that we've done called workspace structuring. What is that? Well, what we've decided to do is say that each post to workspace can be an encapsulated set of inputs, which is usually defined by an input deck. If you have an input deck, let's call that a post to workspace. What we can do now that post is multi-threaded and that we have an API, you can actually use the same post to instantiation to run multiple workspaces in sequence or in parallel. So for example, if you have a problem, a flight mechanics problem, where you're talking about ascent from the moon, you probably want to model that in post. You can use a program like Copernicus to model the interplanetary transfer from the moon to Earth. And let's say you want to model Earth entry, so through the atmosphere down to touchdown, in post. You can now actually do all of that and have Copernicus perform the global optimization across all of these phases, again, using post, the same instantiation of post as the dynamics driver for those phases. So this is really, I think, a really big step in being able to remember that first slide I showed you talking about end-to-end problems. This is really kind of getting to that point where we can treat flight mechanics problems as end-to-end using the appropriate tools, or what we feel like are the appropriate tools for modeling each individual phase. Okay, I'm going to shift gears one more time, and I'm going to get a little bit more into the weeds into an actual application. So most of what I've talked about here is kind of in the software engineering field. We're going to start moving into talking about a more kind of flight mechanics GNC application. And this is actually pulled from one of my papers that I presented earlier this last year now at SciTech 2022. We're going to talk about navigation performance model. So safe and precise landing, what is that? Well, at the moon and Mars for human missions, it's been made pretty clear that we're going to have safe, obviously, and precise landing. So we want to be able to make sure we can land these gigantic vehicles at the appropriate location. And to do that, there's going to have to be pretty decent advances in being able to evaluate GNC technologies. So again, it's guidance, navigation, and control. So there's a particular project, SPLICE, that was tasked to assess these technologies and their performance effects. We looked primarily at deorbit and entry, descent, and landing, that's DDL or EDL. We focused primarily on 6-DOF integrated performance simulations and modeling these GNC systems with varying levels of quality and fidelity. So for example, we were able to look at if you had a really poor IMU, inertial navigation unit, or inertial measurement unit, how does that compare to a really good one? Or if you had a TRN system, terrain relative navigation, that had a really bad camera compared to one with a really good camera? How does that impact performance in an integrated sense? And so what we did is we updated the POS2 framework to have these models, engineering models of these sensors running in the loop with a filter. And so here you can see you have sensors like an IMU, the terrain relative navigation, star trackers, deep space network updates, it's radio navigation, NDL, navigational Doppler LiDAR, that's up here at Langley. We have models, engineering models for all these sensors that feed into an extended counting filter. That's our navigation filter, and that now feeds states and attitudes that go into our guidance algorithms, control algorithms, et cetera. So it's now, we call that in the loop. This is navigation is running in the loop. And so we took this framework and we applied it to a government reference human scale lunar lander and a Mars lander, these entry systems. You can now, because these are built to be generalized, depending on the inputs you put in for these different models, you can have them represent different types of, different models, I guess I should say, different off-the-shelf models of all these different sensors. And it's fast. For these trajectories, we're talking about 10 minutes to run 8,000 sample Monte Carlos. Again, that's from deorbit down to touchdown, 6-stop, all the way with navigation and guidance in the loop. And all of this is documented in these two data. Okay, so I'm going to talk about a particular system, our NASA reference EDL system for Mars. So this is a low lift to drag deployable decelerator. It comes in from a 1-sol orbit. It's a 50-ton entry mass. It's pretty big with a 20-ton payload. We're talking about a 16-meter HIAD and supersonic retropropulsion. So here you can see the kind of general CONOPS that we have where we deploy the decelerator exoatmospherically. We fly through the atmosphere using direct force control and an numerical predictive corrector for guidance, power descent, with 800,000 kilonewton engines, and finally terminal descent. And here I wanted to show you, throughout all these phases, we have models for propulsion. We're modeling RCS, the main engines. We're modeling guidance algorithms, open loop and closed loop. That's the numerical predictive corrector guidance I talked about. Different steering laws, roll control. So we've got control algorithms and actuators running here too. And we've been looking at the system for quite a while. We've published various papers looking at different elements of the systems of this entry system. And what I want to focus on now are the navigation sensors. So keeping in mind that we've already looked at and we've already assessed, or I should say, we've got models for the guidance and control algorithms, the vehicle, the atmosphere, the terrain, the planet. Now we're looking at navigation. And so we've got an IMU, inertial measurement unit. We've got star trackers, low fidelity model, which is really simple, just corrupting truth values for that. Star trackers are running while you're coasting exoatmospherically. IMU is running the entire time. Terrain relative navigation camera, that runs well into entry when you're getting closer to the ground, and a navigational Doppler LiDAR model that's running closer to terminal descent when you're getting pretty close to touchdown. So we have all these different models that are running in our sim. And what we're able to do now is look at performance traits. So this is kind of an eye chart, but what I really want to do is give you an idea of the different kinds of analyses that we can do with these different models that we have. So each one of these rows is an 8,000 case Monte Carlo. So we set up a problem, a simulation to use these different models. And you can see that, for example, we looked at having only a single radio navigation update. We looked at having medium quality. So let's say, better than normal, or worse than normal. I call it ultra DSN, where you say you have, magically good radio tracking, you could get your knowledge, your state knowledge to within, let's say, millimeters per second. What does that do? We looked at ground relative navigation sensor traits. Well, what if you have a, not so great TRN? What if you don't have NDL? What if you don't have NDL and you have a pretty poor TRN system? We can look at all these things literally by just flipping switches and saying, I don't want to run this model. I want to run this one, but with this quality. So each one of these, it's using the same simulation framework. And when you do that, oops. When you do that, let's see if I can bring it back. Yeah, we do that all. Yeah.
I was waiting for the sound.
And when you do that, hopefully this is coming through. When you do that, it's not as cool as the Enterprise, but you are getting you do get some of these results. There's a lot going on here, but I want to draw your attention to is that here I've limited to just 2 cases. The case where we've got perfect navigation. So, we're not worried about sensors at all. We're just running GNC with perfect G and C with perfect states. And then you introduce navigation running in the loop with really high quality DSN estimates. And what I want to draw your attention to is your range to touchdown, which I don't think I said, the goal is 50 meters for Mars, a 50-meter range to target and a 99 percentile sense. With perfect nav, you're at 42 meters, which is really close to that limit. You've already eaten your margin pretty significantly, even with perfect navigation. So when you add all the navigation effects in, you're now seeing 68 meters, which is outside of 50. Well, that's not too bad. Maybe we can do better than that. And the question is how? How can we do better than that? And the other thing I wanted to draw your attention to is this success rate that I'm showing here, which is really the number of cases that we quantified as a safe landing. So landed within a certain attitude rate, velocity relative to the ground, et cetera. And then the percentage is the number of those successful safe landings over the total number of cases, which in this case is 8,000. I'm also showing the amount of propellant used, which is about 10 tons. That's more of just giving you an idea that for these missions, for this particular system, in general, it's about 10 tons of prop to land. Okay, so remember that number, 40 meters, 43 meters, and 68. That's range to target. So now we're gonna look at navigation position error at touchdown. So again, this is all extracted from the same simulation. We ran all these simulations and we can extract all this information from them. In this case, the first column here is the baseline, the one that I talked about with nav in the loop. So that's that 68-meter trajectory. By the time you get to touchdown, your navigation error, you think you're at your position down to 7 meters. Well, if you introduce a median TRN, a median quality, so better, or I should say worse than normal quality, it gets a little bit worse. You get to 12 meters. That's not so bad. If you run that same TRN system, but you don't have NDL, you get a 30-meter error. Well, that's not great, but you look at the success rate and it's now dropped. So because we're able to evaluate these systems in a 6-DOF sense, all integrated, all the way, each one of these samples is an integrated trajectory from deorbit down to touchdown, we're able to understand, did it actually make it to touchdown? Did the navigation error become so bad that it saturated the guidance and control laws such that the vehicle couldn't actually make it to touchdown safely? That's a feature that we can evaluate in post. And so if marching across here, low quality TRN, it's still not so bad. That's really actually NDL cleaning everything up by the time you get a touchdown. Because if you get rid of NDL with a low quality TRN, it just becomes garbage. In fact, the number there, 42 meters, is kind of nonsensical because you've only got 22% of your 8,000 cases that actually made it safely to touchdown. So the point that I'm trying to make here is that we can run all these trades. We can ask questions. Could you use a TRN sensor? Could you add another TRN sensor that works at high altitude, let's say exoatmospherically, without NDL? Would that let you meet your requirements? Could you, there are different questions that we can now ask, and we now have the tools available to help us understand, if not answer definitively. I'm not saying that this is the definitive answer, but it helps us understand the behavior and helps us understand what we need to invest in, what we need to investigate, what we need to do next. So to sum it all up, that's kind of the last thing I had to talk about. I talked about flight mechanics modeling and simulation. We talked about it covering a wide variety of disciplines. The experience that I've had in my branch D205 that is, I think, shared by a lot of my colleagues is that treating these flight systems as in an end-to-end integrated sense can really give you the insight that's needed, we think, to the flight mechanics performance for these increasingly complex systems. Post2 is an example of a flight-validated flight mechanics simulation tool that can benefit from a lot of changes to these advances in computer hardware. And I showed you some updates to the Post2 code base. We talked about making Post thread safe and what that buys us for parallel optimization. We showed you what are very recent developments into the API, which can enable Post being used as the dynamics driver within other applications. And then finally, I talked about the navigation performance modeling updates and what we can do now as a specific application of the whole Post2 program ecosystem. Future work. Perhaps one day there will be a post 3. What will it look like? I don't know. I don't have that answer, but I'm fairly confident that that vertical integration, the developers as user models, is the way to go for post 3 and really going forward for our team. And I have some acknowledgements. I have a group photo of my branch here, taken a few years ago now, pre-pandemic. I'd like to thank my branch management, Ron Mirsky and Monica Hughes, and of course everyone at D205. Specifically, I want to thank the development team and the sport teams for post 2. I couldn't do anything I did here without them. And even more specifically, there are a few folks I want to thank: Jill Prince, Jeremy Scheidner, and Alicia Cianciolo. These are people that I've really looked up to over the years working in D205 that I really try to emulate and model myself after. And then more specifically, big thanks to my mentors, Dick Powell and Bob Tolson. They've been with me since the beginning. Bob Tolson was my graduate thesis advisor, and I still talk to them regularly. I really am not here. I'm not here without them. So my thanks to them and everyone in D205, and thanks to you guys for listening to me talk for 45 minutes. That's all I have. Questions? Yes.
Two-part. How much of your job is developer and how much of it is user? Because you said you. And then the second, in the developing portion of your job, how much of it is kind of the software, hardware optimization kind of piece of it? And how much of it is trying to incorporate new physics, more of the kind of foundational principles that are captured?
So the first question is how much of my time is spent between sort of software development and I guess actual flight mechanic application of these flight mechanics models. It really blurs together. A lot of times I'll be developing, I might be working on developing a physical model for a project. So it's really difficult to kind of delineate between this is the time spent on development, software development, versus the time spent on actually trying to solve some flight mechanics problem. If I had to put a number on it, I'd say it's maybe, I don't know, 40, 60 maybe. And a lot, but again, so I'm giving a little bit kind of a biased answer here because I'm the current post 2 lead developer. So I do spend a little bit more time working with the development team and, kind of working bugs, identifying things like that. The other question was, actually, could you remind me your next question?
How much of, in the development part of your job, how much of that is kind of speed up software, interact with GPUs instead of
the second
that sort of stuff?
Yeah. So the question was versus, within the development part of it, how much time is spent developing new physical models versus kind of working on optimization and speed up, maybe even bug fixes, things like that, maintenance, if you will. And the answer is that is kind of that blurs together too. The development team meets every other week. We go over bugs that have come up that we get reports on. And in terms of new models, new features, that really comes from the projects. So if a flight project that we're supporting, that my branch supports, needs a model for a rotor system, for example, maybe that's something we don't have in our library of tools and models. That's something we need to create. And so in those kinds of situations, we'll go to a subject matter expert. We'll go to the people in the know for those kinds of systems and say, hey, what's the best way we can model this kind of physical system? And how do we turn that into an engineering model? And so to break it down, it's probably, I don't know, 50-50, 60-40 again, maybe. It's tough to put a number on. Yes.
My proposal to support atmospheric flight, especially when say automated atmospheric flight.
So the question was, can post 2 support automated atmospheric flight? I think the answer is yes. So it was originally built for shuttle entry. It's used extensively for kind of the bread and butter in my branch is EDL. So we're talking about things like capsules. It's used extensively for ascent launch vehicles. But it's been used in other applications for fixed wing aircraft. The traditional jets and things like that. There's really, provided that you have descriptions of the aerodynamics and the control laws, there's really no reason why you can work on that kind of problem. Yeah. Yes.
Yeah, my question was, when you're talking about developing new models, Do you mean that, like, if you use the rotor case or something, is that where you kind of say, okay, what's out there that maybe models that exist and we just link to them with our existing software, or are you actually like changing those two?
That's a really good question. The question was when we're talking about new models, new features, do we link to them, or are we talking about actually changing code within the Post2 framework itself? That answer has actually changed over time. 15 years ago, the answer would be yes, we would have had to modify Post2 code to be able to ingest a model like that. But over time, what we've tried to do over the past 10, 15 or so years, maybe even more, is try to move to a more modular approach where if we can create, basically I talked about going to the subject matter expert, we create a model that's kind of Post2 independent. We want some, it's got inputs and outputs. Let's say outputs are forces and moments. We've built in the hooks now, and we've modularized the Post2 core software such that it links up fairly seamlessly. We really don't have to modify the core code. Any other questions?
So 2 software engineering related questions, but how are you finding the bugs and who are supplying those? This follow-up question is, who's performing the validation verification?
So the first question was who's finding bugs, and the answer to that is really anyone that uses.
Assuming there are bugs, by the way.
Oh yes, that is a very safe assumption. Yeah, there are definitely bugs in Post, and it's really users. We have, like I talked about, we have users in industry, academia. We have a Post2 help desk email that we get regular, messages to. We have people in the branch. Our branch, I would say, our branch D205 is probably one of the heaviest users of Post, unsurprisingly, and so we find things that we have to fix. So we'll bring it up in our development team meetings. The question was verification and validation. I presume you mean of physical models?
Yeah, physical models, software.
Yeah, so we do. I talked about Post being flight validated. I say that because it's been used extensively on flight programs, on flight projects, going all the way back to shuttle. So over the years, one of the I would say advantages maybe that Post has over perhaps other tools is that it's been around for so long. We have built up a pretty big suite of test cases that we run and that we perform regression tests against. When it comes to new models, so I should say that means we're pretty confident, like the equations of motion. We're pretty confident that the integrators, the EOMs, those work and are correct. When it comes to V&V of new models, it really depends on the flight project. If it's a research project or a proposal, we might be using models that are more, we built for a particular project. Hey, Sam, you built a model that you're using on your project. You're doing something similar to my project. Can I borrow it? And because it's all modular, we can do things like that. But when it comes to things like flight projects, what will typically happen is we will get code that is delivered to us, like the GNC package, the flight software. And so depending on kind of the project we're doing, if it's an NESC project, we might be in the business of IVNV, performing IVNV ourselves. If we're in the business of, say, some other project where we're doing analysis with some other group's code, we rely, like I said, we work very closely with the authors. I don't know if I answered that question very well. Did I answer both of your questions? Okay. Any other questions? Yes, back there.
You mentioned Post3 a while ago, and I may have missed this in your talk, but how is it going to compare with Post2? What are like the big advances within Post3?
Unknown. We've talked over the years. There's always been talk of, well, what's Post3? What is that going to look like? Some might argue that the one of the more recent, the 4.0 series, we almost called that Post3 because that was such a I wouldn't say a radical departure, but it was an overhaul, a really heavy overhaul to get to that modular point. And so I don't have an answer. A lot of it depends on how much money we get for development. We don't really get a lot of money for development, but we try to maintain and support flight projects as best we can. So I don't have a good answer for that because we don't know.
Okay, thanks.
Yep. Any other questions? Yes.
So kind of back to the verification validation question. Do any of the Post projects have to adhere to NASA standard 7009 credibility assessments? And if so, do you like maintain a set of artifacts
Right.
with post2 to help with those assessments?
So I'm not as familiar with 7009. I think there is there are the standards like, for example, post is class C, or I'm sorry, class D, non-safety critical. So the software, the core software itself is certified to, to that extent. When it comes to 7009, I might need to rely, yeah, some.
The answer is yes. For some projects, we have to do that, and it depends on the mission criticality aspect of it too. But there are projects that adhere to the NASA standards and maintain artifacts. That is a
Yeah, so if for those online who couldn't hear, some was saying that it depends on the project. Some projects need to adhere to 7009 standards, and that in those situations we work, with the project program to do that. Did that answer your question?
Yes.
Yes.
Keep looking at me, Anthony, sorry. Class D, that's interesting. So do you use this software for just planning what's going to happen, or is it actually, so is it not actually used like during flight? It's just used for planning what?
We have to be very careful about how we frame that. Because it is class D, non-safely critical, we don't use, it's not used on board for anything. It's not used for, real-time on-orbit operations, that sort of thing. Now, having said that, very often we support mission operations to be able to provide additional information to mission planners. So it may not be impacting mission performance directly in most cases. It is used as an informational aid, and some. I think
yeah. The term is it's used for decision making.
Yeah.
Like before.
That's partly probably we don't want to be class C, so that's probably very much emphasizing that as the dev lead. But we do support operations, but no answer from post directly goes into the flight system. There's always humans in the loop. And
yeah, and if you want to think about it this way, for a lot of these flight missions, there is the tools and systems they have already designed to construct the gain schedule or things like that that get uploaded to the spacecraft. Post might be used to check those or say your numbers should look like this perhaps, but it's not used to actually generate values that get pushed to a spacecraft. So that's how we get away with being class.
And I guess last follow-on question for that. And so post2 is also not used to be the official verification of record for requirements when verifications have finances.
My work with HLS is making me sweat with these questions.
Class C,
Yeah.
you do that.
Yeah, no, so what I can say is that we have been through NESC, we've
Can you repeat the question?
oh yes, repeat the question. I heard requirements and I started plot sweating and
So it's not used to provide the qualification of the system against its requirements when those requirements are verified by analysis.
yes, so the question, if I'm going to try to throw that back at you, you're asking about the possible usage of post in verifying requirements for a program. I think Sam has an additional answer to this. I think I would say that it probably depends on the program. If it's like a research or pre-phase A system, like a proposal, for example, it might be used differently than in a program. So for example, SLS, we perform IB&V through NESC for SLS. We're using the SLS flight software that the program has provided to us to do trajectory analysis, but we don't impact. We help inform the program on their requirements, but it's not used for requirements verification for programs like SLS. Sam?
well, and I would say this: Rafael and I have very different experiences in the projects. He has been working with the NESC side way more, and his statement is absolutely correct. It's IB&V. I work more on the planetary exploration system side, so on the Mars missions, on the planetary missions, post is the answer we are using for, like we are the prime sim that's getting used for answering the requirements. So it really depends on which one of us you ask that question, but for the Mars 2020 project, those answers were used to figure out what the settings should be on the actual spacecraft. And we are answering requirements. In fact, we had a V&V exercise, that was happening before launch and went into launch to figure out all the flight artifacts, and that was tested using those. So it really is different on different sides of the world. I think we're trying to work through Rafael and others, on the human landing side, we're starting to have impact with Toast on that side, but on the planetary exploration side, especially robotic exploration side, Toast has been the standard for
Yeah,
decades.
and for those online, to sum up Tom's response, it's again project dependent. For Mars missions, it's been the standard to use Post, and I think to tack on one more piece to that, a lot of that is because that was what it has been used since way before 7009 even existed. So in some ways, we've gotten away with grandfather status. Our relationship with JPL for Mars missions has been very close since, well, really since Viking and onward. But like I talked about with Pathfinder, before 7009, before all these standards were even written, we were using Post for that sort of. Okay.
I'll ask another question.
Okay. Well, at 12:30, I'm happy to talk to you after. Yeah, I'm happy to stick around if anybody has any other questions. But I have 12:30, so I guess I'll
Ask questions on the chat.
Okay. Well, thank you guys. I appreciate it.
For the environment, there's a can and bottle recycling just around the corner of this trash